Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
In ancient Greece, discovering a number that just didn't end could literally get you assassinated.
Which is, a pretty extreme reaction to math.
Right. I mean, usually when we talk about things like a medical diagnosis or, I don't know, building a bridge, there's this expectation of absolute precision.
Oh, absolutely. Like, you want your engineers to be exact.
Exactly. Like, you break your arm, the x-ray shows that jagged white line, and the doctor points and says, there it is, exactly there. But today, we're diving into something that entirely breaks that kind of clean, visible logic.
It really does. It's unsettling.
Yeah, we are talking about something that in Latin literally translates to without reason. So welcome to our deep dive into the infinite, mind-bending, and honestly, historically dangerous world of irrational numbers.
It is a world that has deeply unsettled some of the greatest minds in history. And honestly, it still challenges how we conceptualize the universe today. I'm very excited to guide you through it.
I am too. And to tackle something this massive, we're going to slightly adjust our dynamic for this deep dive. I'm going to enthusiastically step into the role of the curious student today.
I like it.
Yeah, I'll be the one asking these seemingly obvious questions, stumbling through the infinite decimals and, pushing back when the math starts sounding like pure magic. And you, my friend, are going to be our lecturer.
Well, I happily accept the role of lecturer. I'll do my best to keep us grounded while we stare into the mathematical abyss.
Perfect. So our syllabus for today, the foundation for our entire journey, is section 3.5 of chapter 3 from Contemporary Mathematics.
A great text.
Yeah, we're pulling all our structural insights directly from it. And lecturer, I have to start with the hook you find in this material because it is absolutely wild. It opens with the Pythagoreans.
Ah, yes. The ancient Greek philosophical sect. Most people today, just know them for that geometry theorem about right triangles we all had to memorize in middle school.
A squared plus b squared equals c squared.
Exactly, but they were so much more than a footnote in a geometry textbook.
They were essentially a math cult. I mean, the text points out that their whole philosophy centered around reincarnation and, purifying the mind by contemplating science and math.
Right. They literally believed the cosmos was ruled by order, specifically mathematics and music.
Which is wild. They assign these heavy mystic meanings to basic numbers. Like the number 1 was the mind in essence, and the number 4 represented justice, basically because it was the first product of 2 even numbers.
Right. They had built a complete worldview, a religion really, on the foundation that everything in the universe could be measured, categorized, and expressed perfectly as a ratio of whole numbers.
So everything was fractions to them.
Basically, yeah. If you have a string of a certain length and pluck it, it makes a sound. Cut that string in exactly half, so a clean 1-to-2 ratio, and it makes the same note, just an octave higher.
Oh, that makes sense.
Yeah, they looked at that and thought, the universe is fundamentally neat and tidy. God is a mathematician.
Okay, let's unpack this, because if I'm understanding this right, its obsession with neatness wasn't just a preference. It was like their moral compass.
Exactly. It was foundational to their reality.
Which leads to what might be history's first math-related murder mystery.
Yes, this is a great story.
The textbook shares this incredible story about a Pythagorean named Hippasus. Legend has it, he was just messing around with a simple square, measuring the diagonal line across it, and he discovered that the length of that diagonal could not be expressed as a clean, tidy fraction.
He found a number that was messy and endless.
Right. And supposedly the other Pythagoreans were so horrified by this discovery that they took him out on a boat and drowned him at sea to keep the secret from getting out.
It is a phenomenal, albeit, very dark story. Now, as Section 3.5 carefully notes, we do have to look at this through a historical lens.
So it might not be true.
It is most likely false. There are no contemporary sources from that specific era to actually corroborate a mathematical assassination at sea.
Bummer. I mean, not for Hippasus, but for the drama.
Right. But the reason the story survives, and why it's so crucial to our understanding today, is that it perfectly marks the sheer earth-shattering magnitude of discovering irrational numbers.
Because it broke their whole worldview.
Exactly. Hippasus proved that their perfect measurable universe had an underlying layer of unmeasurable chaos. He shattered their illusion.
Man, the idea that a number could be so terrifying that people might invent a murder myth about it. I mean, as your student, I have to ask the basic question. What exactly makes a number irrational?
That's the perfect place to start.
Like if I'm looking at a number, what makes it so revolutionary?
Well, let's define our terms clearly. To understand the irrational, you first have to understand the rational. A rational number is any number that can be expressed as a fraction of two integers.
So whole numbers over whole numbers, like 1/2 or 3/4 or 5/8.
Precisely. And when you convert a rational number into a decimal, it behaves itself. It does one of two things.
Which are?
Well, it either terminates completely, like 1/2 simply becoming 0.5, or it falls into a predictable repeating pattern.
Oh, like 1/3.
Exactly. Think of 1/3, which becomes 0.3333 repeating forever. Even though it goes on forever, it has absolute order. You always know what the next digit is going to be.
Okay, got it.
An irrational number, by contrast, is a number that absolutely cannot be expressed as a fraction of two integers.
And what does that actually look like if you try to, type it into a calculator?
It means the decimal representation never terminates, and it never, ever falls into a repeating pattern. It just goes on forever, constantly changing, completely devoid of predictable order.
So if a rational number is like a pop song, it has a clear 3-minute ending or maybe a repeating chorus that you can easily sing along to, even if it fades out, an irrational number is like a chaotic jazz solo.
I love that.
It just keeps going and going forever, never repeating a phrase, constantly unpredictable, and there is absolutely no sheet music that can perfectly capture the whole thing.
That is a brilliant analogy. It is a mathematical jazz solo that never resolves. Now, the textbook provides us with two main categories to help us identify these infinite jazz solos in the wild.
Okay, what's the first one?
The first collection is the square roots of numbers that are not perfect squares.
Right. Perfect squares are the easy ones I remember. Like the square root of 9 is 3, the square root of 16 is 4, because 3 times 3 is 9, and 4 times 4 is 16. Clean and tidy.
Exactly. The text notes a mathematical way to check this. If you look at an integer's prime factorization and all the prime factors are raised to even powers, you have a perfect square.
And if it doesn't?
If it doesn't meet that strict criteria, its square root is irrational. The text even gives a modern practical tip. You can use a digital tool like the Desmos keypad, specifically the square root key, to test a number.
Okay.
If you plug it in and it doesn't give you a clean integer back, but instead spits out a long, messy decimal, you're looking at an irrational number.
But wait, let me push back on this a little bit. Let's take the square root of 5. It's roughly 2.236. Why can't I just say, you know what, 2.23 is close enough?
Because it's not the exact value.
Right, but why do we have to treat this infinite non-repeating decimal as this special untouchable category? Why not just round it off and move on with our lives?
Well, because rounding is an estimation and mathematics is about absolute truth. If you are building a wooden bookshelf in your garage, rounding the square root of 5 to 2.23 is perfectly fine.
Sure, my books won't notice.
Exactly. But if you are a NASA engineer calculating the orbital trajectory of a satellite slingshotting around Jupiter, you can't round off. That tiny, missing, infinite tail of the decimal will compound over millions of miles until your satellite completely misses the planet. You need the exact value.
Wow. Okay, that makes sense. The universe cares about those hidden decimals even if my tape measure doesn't.
It really does.
And that leads perfectly to the second category the textbook gives us, which is the most famous irrational number of all time, pi.
Yes, denoted by the Greek letter. Pi is the fundamental ratio of a circle's circumference to its diameter.
And this is where it gets crazy to me. No matter how perfect a circle you draw, whether it's a wedding ring or the equator of a planet, if you try to divide the distance around the outside by the distance straight across the middle, you get an irrational number.
Yeah.
3.14159 and on into infinity, never repeating.
Right. And section 3.5 points out that any multiple or power of pi is also irrational. 2 times pi is just as endlessly chaotic as pi itself.
What's fascinating here is how these numbers interact with the clean, rational numbers we're used to.
Oh, this is the best part.
Like, if I have a perfectly clean number, like 10, and I add pi to it, it becomes 13.14159 continuing forever. The textbook points out that if you take any rational number and you add it to an irrational number, or subtract, multiply, or divide it by an irrational number, the result is always irrational.
Yep.
It's like the chaos is contagious.
It is entirely contagious. A single drop of irrationality turns the whole equation into an infinite decimal. The text calls this creating a number with a rational part and an irrational part.
But the whole thing is still a mess.
Exactly. Make no mistake, the overall value itself remains infinitely messy.
Which brings me to the massive practical problem here. If pi and these weird square roots act like a contagious virus that makes decimals go on literally forever, How on earth do engineers actually build perfect cylinders for rocket ships without their computers crashing from an infinite calculation?
That is the pivotal question.
Like, if I try to plug the true value of an irrational number into an equation, won't I just run out of paper or screen space?
How do you hold infinity in your hand without it crushing you? The secret to wrangling this chaos is that we simply don't write out the decimals. We lock the infinity inside a box.
A box.
For square roots, we simplify them by keeping the square root symbol perfectly intact. The number inside that square root symbol has a specific name. The text calls it the radicand.
The radicand. Okay, I'm writing that down in my notes. So the symbol acts like a cage.
Exactly. To simplify a square root without losing its exact value, we rely on a fundamental formula. The square root of a product, let's say A times B, is exactly equal to the square root of A multiplied by the square root of B.
Okay, lecture, let's test this. Let's walk through one of the actual mechanics so I can see how we tame this chaos.
Let's take an example straight from the material, the square root of 180.
Okay.
If we type that into a calculator, we'd get a horrendous infinite decimal. We want to avoid that. So we need to find the largest perfect square that divides evenly into 180.
Okay, let me think. 180. Well, it ends in 0, so 10 goes into it, but 10 isn't a perfect square.
Right.
9 goes into 180, 9 times 20. And the square root of 9 is 3. So is the answer 3 times the square root of 20?
You are on the right track, but 20 still contains another perfect square hidden inside it. What goes into 20?
Oh, 4 goes into 20, and 4 is a perfect square. So I didn't find the largest perfect square initially. Let me recalculate.
It's your time.
If 9 works and 4 works, 9 times 4 is 36. Does 36 go into 180? Yes, 36 times 5 is 180.
Spot on. So we rewrite the original problem, the square root of 180, as the square root of 36 times 5.
Okay.
Using our formula, we split that cage into two separate cages. The square root of 36 multiplied by the square root of 5.
And since 36 is a perfect square, the square root of 36 completely escapes the cage and just becomes the clean integer 6.
Exactly. So your final simplified answer is 6 times the square root of 5, or simply 6 root 5.
Wow, okay.
You now have a rational part, the 6, and an irrational part, the square root of 5. You have expressed the number in lowest terms, maintaining absolute, perfect mathematical precision without ever having to write out an infinite decimal.
Okay, that feels strangely powerful. I've basically compressed an infinite string of numbers into a tiny icon. But let me challenge this. What if I want to do basic arithmetic with these icons?
All right, what do you mean?
Can I just add any two irrational cages together? Like, if I have the square root of 3 and I want to add the square root of 5, is that just the square root of 8? That seems logical.
It might seem logical, but it is absolutely incorrect. And this is a very common trap.
Really?
Yeah. When it comes to addition and subtraction, the rules are incredibly strict. The irrational parts, the cages themselves, must match exactly. They have to be similar.
Why? Why can't I combine them?
Think of the square root symbol like a unit of measurement, like apples and oranges. You can't add 3 apples and 5 oranges and say you have 8 apple oranges. They are fundamentally different things.
Okay, so what does that mean in practice when we are looking at an equation?
Let's use an example. Imagine you have 3 times the square root of 7, and you want to subtract 8 times the square root of 7.
Okay.
Because the irrational parts, the square root of 7, are identical. They're the same fruit. So you just perform the math on the rational numbers sitting outside the cages.
So 3 minus 8 is negative 5.
Right. So the exact answer is negative 5 times the square root of 7.
Got it.
But if the irrational parts don't match, like your earlier example of root 3 plus root 5, you cannot combine them. You just have to leave them sitting next to each other as a statement of addition.
Okay, so addition and subtraction are super strict. But what about multiplication and division? Are they just as rigid?
Not at all. Multiplication and division are much more flexible. The irrational parts do not need to match.
Oh, really?
Yeah. The formula states that you simply multiply or divide the rational parts together on the outside, and then multiply or divide the irrational parts together on the inside of the cage, and then simplify whatever you are left with.
Let me see if I can synthesize this. So what does this all mean? It means we are basically treating these infinite, messy, chaotic decimals exactly like variables in algebra, like an x or a y. That's a great way to look at it. Right. As long as we keep the chaos locked inside its little square root symbol, or as the pi symbol, they behave predictably. We don't have to look at the infinite decimal, we just move the symbol around the board according to the rules of algebra.
That is a perfect synthesis. You are isolating the infinite so that you can still perform exact, precise mathematics on the real world without losing your mind.
Okay, I'm feeling pretty confident I can wrangle infinity. But there's a conceptual problem that the textbook brings up next that genuinely scrambled my brain.
Let's hear it.
It has to do with fractions. The text says that, conceptually, a fraction represents dividing a whole amount into a certain number of equal parts.
Yes, that is the foundational idea of a fraction going all the way back to elementary school.
Right. If I have a pizza and the denominator is 4, I am physically dividing the pizza into 4 equal slices. I can visualize that. I can hold it in my hand.
Sure.
But what happens when the denominator of a fraction is an irrational number? How on earth do I divide a pizza into the square root of 2 equal slices? That makes no logical sense. You can't divide physical matter into a non-repeating, infinitesimal amount of groups.
You've hit on a major conceptual roadblock. An irrational denominator breaks reality. It interferes with our fundamental interpretation of what a fraction is supposed to be.
Okay, so what do we do?
Well, that is why mathematicians had to invent a workaround. The text introduces a process called rationalizing the denominator.
Rationalizing the denominator. Okay.
We have to perform a mathematical magic trick to force that irrational chaos out of the bottom of the fraction, moving it somewhere where it makes sense again.
But how do we do that without changing the actual value of the fraction itself? If I start changing numbers, I ruin the calculation.
We use a very clever ancient property of fractions.
Yeah.
If you multiply the numerator on top and the denominator on the bottom by the exact same non-zero number, the overall value of the fraction remains completely unchanged.
Oh, because you were essentially just multiplying the whole thing by 1.
Precisely.
Okay, I remember that from basic math. 2/4 is the same as 1/2.
Exactly. So if your problematic denominator is just the square root of 7, you simply multiply both the top and the bottom of the fraction by the square root of 7.
Oh, I see. Because based on our multiplication rules, the square root of 7 times the square root of 7 is the square root of 49.
Right.
And 49 is a perfect square, which simplifies down to just a clean, beautiful 7. The square root cage essentially annihilates itself.
It does.
The bottom becomes a clean, rational whole number, and the messy square root just gets moved up to the top of the fraction, to the numerator, where it isn't conceptually bothering us anymore. Dividing a messy number into 7 equal slices makes perfect sense.
Exactly. You've successfully rationalized it. But as your lecturer, I must warn you, the textbook takes this a step further into much more complex territory.
Here's where it gets really interesting. What happens when the denominator is a mix?
What do you mean?
The textbook is an example where the denominator isn't just a single square root locked in a cage, but an entire expression, like a rational number plus an irrational number. The specific example given is 5 divided by the quantity of 4 plus the square root of 3.
Yes, 5 over the quantity 4 plus the square root of 3. If you try our previous simple trick and just multiply the top and bottom by the square root of 3, you run into a wall.
Why is that?
Because of the distributive property, you have to multiply both parts of the denominator. You'd end up with 4 times the square root of 3 plus 3.
Oh, so the square root didn't disappear, it just multiplied itself to the other number. The chaos just hopped over to the left. I'm still stuck with an irrational, impossible denominator.
Precisely. The simple trick fails entirely.
So what's the advanced trick? How do we break this?
If we connect this to the bigger picture of algebra, we have to borrow a concept called the conjugate.
The conjugate.
Yes. I want you to think of the conjugate like a mathematical mirror image, or maybe even antimatter. The conjugate of an expression like A plus B is simply A minus B. You keep the exact same numbers, but you just flip the sign in the very middle.
So in our textbook's specific example, the denominator is 4 plus the square root of 3. That means its exact mirror image, its conjugate, would be 4 minus the square root of 3.
Exactly. And this is where the pure magic of mathematics happens. When you multiply a binomial expression by its conjugate, when matter collides with its exact antimatter reflection, it triggers something called the difference of squares.
Okay, I'm listening.
You don't just shift the chaos around, you force it to collapse in on itself.
How does that work without us doing a bunch of tedious algebra aloud?
Think of it visually. When you multiply these two reflections together, the outer edges of the equation square themselves into clean, normal numbers.
Right.
But the messy, irrational parts in the middle, because one is positive and the exact mirror image is negative, they perfectly collide and cancel each other out. They annihilate each other, leaving nothing but 0 behind. The chaos simply vanishes.
Let me visualize that with the numbers. If we take our bottom part, 4 plus root 3, and multiply it by its reflection, 4 minus root 3, the outer edges square themselves. So 4 squared becomes 16.
Yep.
And the square root of 3 squared just becomes a clean 3. And those messy, chaotic middle parts that usually ruin everything just fold in on themselves and disappear entirely,
They vanish as if they were never there.
leaving us with just 16 minus 3, which is 13. A clean, rational, perfectly normal integer sitting right there in the denominator.
It is brilliant, isn't it? By multiplying both the top and the bottom by that conjugate reflection, the impossible, irrational denominator is wiped out of existence.
That's incredible.
It leaves you with a fraction you can conceptually understand again. You can confidently divide a pizza or a rocket trajectory into 13 equal parts.
Okay, lecturer, consider my mind officially blown. I'm going to drop the student persona for a second to talk directly to you, the listener. We just went on an incredible journey through section 3.5.
We covered a lot of ground.
We really did. We started with an ancient Greek cult assigning the moral concept of justice to the number 4 and discovering numbers so fundamentally terrifying they allegedly committed murder over them.
A dark but fascinating start.
Right. We learned exactly what these irrational numbers are. Infinite, non-repeating decimal jazz solos that refuse to follow the sheet music. And most importantly, we learned how humanity figured out how to tame them.
The wrangling of infinity.
Exactly. We learned how to lock them in cages to simplify them, and how to use mathematical mirror reflections to literally erase them from the bottom of our equations so the universe makes sense again.
It really is a sweeping journey from ancient religious philosophy to rigorous modern engineering. And the real-world value here, the reason this matters to someone wanting to be truly well-informed today, is about understanding the very boundaries of human logic.
How so?
Well, rational numbers work beautifully for everyday things, cutting a pizza, counting your change at the grocery store, balancing a checkbook. But irrational numbers, they govern the physical geometry of the universe.
The big stuff.
Exactly. They dictate circles, spheres, triangles, and waves. Learning how to manipulate them, how to keep them perfectly exact without losing our own minds to infinity, is a profound exercise in critical thinking. It proves that we can invent tools to handle concepts that literally break our standard ways of measuring reality.
It's about humanity finding order, or at least a working system, inside of pure chaos.
Exactly. We build a cage for the infinite. And the textbook actually leaves us with one final incredible thought in its Who Knew section that perfectly encapsulates this feeling.
Oh, the Euler-Mascheroni constant? Yes, please share this. It blew my mind when I read it.
It raises such an important question about what we think we actually know about the math we use every day. Determining if a number is rational or irrational is not always as easy as hitting a button on a Desmos calculator.
Right.
The text brings up the Euler-Mascheroni constant. It is a vital, foundational mathematical function used primarily with natural logarithms.
And just for context, logarithms aren't just abstract math. They are used in everything from calculating the compound interest on your bank loans to measuring the devastating magnitude of earthquakes on the Richter scale. It's real-world stuff.
Very real world. It is a fundamental constant of modern mathematics. Now, mathematicians have known about this specific constant since the year 1790. They have been plugging it into complex equations for centuries to build the modern world.
Which is a long time.
But it wasn't until the year 2013, over 220 years after it was discovered, that mathematicians finally managed to prove definitively that it was an irrational number.
That's insane. Over 2 centuries of humanity using a number every single day without fully knowing its true nature. We were building things with it while having no idea if it ended or went on forever.
Which leaves you with a rather profound thought to mull over long after this deep dive ends. If it took the greatest mathematical minds on Earth 220 years to figure out a constant they use literally every day to measure reality, what other fundamental truths about our universe are sitting right in front of us?
It makes you wonder.
Exactly. What else are we using every single day, just waiting centuries for someone to finally figure out what it really is?
Or, to bring it all the way back to the beginning, what other messy, infinite truths are quietly hiding inside the clean, visible logic we so desperately want to believe in? When you realize how much of the universe is built on endless chaos, well, it kind of makes you understand why the Pythagoreans were so scared of the water, doesn't it?